We're going to start off really, really difficult here. Are you guys ready? Sound not ready since you're all silent. I am driving a car for 2 hours. That's a long time. There's my graph of my velocity function. My velocity is 60 miles an hour. I drove from t equals 0 to t equals 2 hours. How far did I go?
120 miles.
Seems reasonable. Would you all agree with that?
Yeah.
Oh, good. I hope you agree with that because that's right. Wonderful. Let's do another one. Like I said, we're going to start off really difficult. Now I drove my magical car at exactly 60 miles an hour for 1 hour. And then instantaneously, because the car is magic, my velocity increased to 70 miles an hour. I just snapped my fingers and was then going 70 miles an hour for the next hour. And how far did I go in those 2 hours?
130.
Nice, well done. Those of you that don't like to participate, this was your chance to participate and get those answers right. Nice, easy questions. Any questions on those two so far? Oh, good. All right. Let's look at another one. Now, somehow I'm starting at 60 miles an hour and I'm going to 70 miles an hour. And I'm doing that over 2 hours at a constant rate. And the acceleration happens at a constant rate. I'm not stepping on the gas and then slamming on the brakes. I'm constantly accelerating over 2 full hours from 60 to 70 miles an hour. How far did I go?
$130.
How'd you get 130?
I just thought because if you're increasing at a constant rate, you could just do like the average, which is 65 times 2, right?
That seems reasonable, right? The average of 60 and 70 miles an hour is 65. Multiply it by 2. Should get 130. Yeah? Everybody agree with that?
Yep.
Wonderful. All right. Now's where things start to get a little more complicated. Now I'm traveling at a variable rate from t equals 0 to t equals 2 hours. Maybe the fastest I ended up going was 70. The slowest I ended up going was 50. I increased, then I kind of flattened out for a little bit, then I decreased, and then I sort of decreased a little more slowly. Then I increased pretty rapidly again, and then sort of tapered up. Then I did I had some weird driving habits, clearly. Yeah. So how far did I go? Silence. Good question, right? Who knows? I mean, there's no way to really know exactly how far I went, right? There's no information to tell me exactly how quickly I was speeding up or exactly how fast I was going at every instant in time. True?
Yes.
Yeah. All right. So what we're going to do before we try to figure this out is we're going to come back to the beginning here. This is the first one we did. And how is that 120 miles related to the graph that I've drawn? Is it related to it in any way?
It's 60 times 2.
It's
Which is
60,
the
which
area.
is this height, times 2, which is this width, right? It is if I were to just make this into a rectangle, right? It's just the area of the rectangle, isn't it? All right, well, what about this one? This one was different, right? I have two different rectangles, don't I? What's the area of the smaller rectangle?
60,
60,
60. What's the area of the bigger rectangle?
70,
70,
70. Add those together, you get 130. It was just the area underneath my velocity function. Right, what about this one? The one that we were pretty sure was 130, but we weren't like 100% positive. Right? Well, the area underneath this is just a trapezoid, isn't it? Two parallel bases. So find the average of the bases and then multiply that by the height. So what's the average of the bases? That's 60 plus 70 over 2, and multiply it by the height. And what do you get? You get
130.
130, exactly what we were looking, right? Exactly what we thought it should be. Okay, so that's good news. All right. What about this one? What should the total distance that I traveled be? I mean, we had miles per hour for all the other ones, right? And the velocity, and we multiplied it by hours, right? Which is why we should get miles if we do that, right? Miles per hour times hours, looking for area, should become miles. So what's the area underneath that curve? Good question, right? We don't have an area underneath that curve. And it's not a nice little trapezoid or a rectangle or a couple of rectangles or squares or something that I can easily find the area of. So maybe we could find a way to approximate that area. Anybody have an idea of how we might approximate that area?
I don't know, kind of like an average slope of the line or something like that.
Okay, an average slope of the line. Okay, so so like from here to here or something, and then trying to figure out different pieces of it. So like break it down into different little geometric pieces where we could find it. Is that what you mean?
Yeah, something like that.
So let's look here. What geometric piece did we use here?
rectangle.
Rectangle.
And a rectangle here. So maybe we could try a rectangle. How could I draw some rectangles in underneath here? There's a rectangle. I could find its area, right? Here's another rectangle. Here's another rectangle. Here's another one. Could I find the areas of each of these rectangles?
In theory, yes.
In theory, yeah. That'd be really irritating though, wouldn't it? Yeah. It's like, I don't know what it's like. It's like something, yeah. Bunch of little rectangles on. That'd be really, really irritating. So it'd be nice if maybe we had like a uniform way to draw some rectangles on here. And that's what we're going to do. We're going to talk about today 3 different ways to approximate the area underneath the curve, and they're all going to use rectangles. And they're all exceptionally similar to each other, and they're all pretty straightforward. The first one is called a left rectangular approximation. And you might at some point hear this referred to as a left Riemann sum. And we'll talk more about that terminology and what a Riemann sum really is as we get further into what we're doing for this unit. But the left rectangular approximation method says, take your interval. We have an interval from 0 to 2 hours, right? And break it up into however many little subintervals you want. So I've broken it down into 8 little subintervals, right? 4 for each hour. And it says, well, take the leftmost endpoint of your entire interval, find the point on your function there, and draw a rectangle only in the first subinterval. Then do it again, except now your rectangle should be at the height of the beginning of the second subinterval, so here, and go straight across and down. And then it says, well, do it again. Go up to the next height. I lost my pen. That's not good. And now my toolbar is not there. All right. So then go up to the next one and make the next rectangle, and then do the same at each of these subintervals. Go to the height at that beginning point, the left point of each subinterval, and draw a rectangle. And what do we notice here? First off, we should hopefully notice that if we knew what each of these y values was, we could find the area of each of these rectangles and sum them all together fairly easily. True? Wouldn't it be pretty easy to sum those all together?
True.
Yes.
Okay, good. But only if we knew the heights of each of them. And next thing we might note is that some of those rectangles leave some space off, don't they? True?
Yeah.
Missed me. We might note that some of those rectangles go a little bit over. True? And we would say, well, some of this extra green will fill in some of these gaps where we're missing some of the yellow. It won't do it perfectly, but we could get a decent approximation of this function, right? And it's the area underneath its curve. And we might note that anytime f was increasing, what happened with our rectangles? They gave us an area that was less than the actual area, right? F was increasing, then we had an underestimate. And if F was decreasing, we got an overestimate. True?
True.
Sure.
All right. And how accurate do you think this is? Do you think this is a pretty accurate estimate or not that accurate?
Fairly accurate.
Fairly accurate. What do you think would make this estimate even more accurate?
If we decrease the intervals,
If we decrease them, you mean instead of having them be a quarter of a unit
the
each, make,
length of the intervals, I mean, like make more
yeah, make more subintervals, right? Make more rectangles. So instead of having 8 of them, have 16 of them, or instead of having 16 of them, have 100 of them, right? Suppose I had 1,000 subintervals inside of here. Well, the little tiny bits that I was under would be very, very, very small and insignificant. And the little tiny bits that I would be over, if I had 1,000 subintervals, would also be very, very tiny, very, very insignificant. And so if we were able to do, let's just say 1,000 subintervals, we would have a value that would be exceptionally close to the exact area underneath the curve. Would you guys agree or no? Yeah? No? Maybe?
Yeah.
Cool. All right, great. So let's keep that idea in the back of our minds for today and tomorrow, and move on to the next way that we're going to approximate one of these. And it's going to be almost exactly the same. It's called a right rectangular approximation, or a right Riemann sum. And guess what you do? Instead of using the height at the left endpoints, you use the height at the
Right.
right endpoints of each subinterval. So generally when I do this, I start drawing from the right-hand side, but you don't have to. You can draw from the left-hand side and just say, all right, there's the right end of that interval and there's the rectangle, but I generally will start drawing from over here just because I feel like it makes life a little easier. Good or no? And once again, we might note that there are some sections that go a little over, and there are some sections that we don't quite get enough area. True? True. Oh, I forgot to draw there we go. And we might notice that when our function is decreasing, apparently I'm on the highlighter now. When f is decreasing, we get an underestimate for these. And when f is increasing, we get an overestimate. Good or no?
Good.
All right. And this stuff about whether it's increasing and it's an underestimate or decreasing and overestimate for the left and the right Riemann sums, or the left and the right rectangular approximations, that's fairly an important idea. You definitely want to remember that because they will ask you about that on the AP test, almost certainly. If they ask you to do a left or a right rectangular approximation, they will give you a function that is either always increasing or always decreasing, and they'll want you to tell them whether or not the approximation is greater than or less than the actual value of the exact area underneath the curve. So just make a note that those are important things to know. And this is a decent approximation, but once again, how could we make this approximation a lot better?
Smaller intervals again.
Yeah, smaller intervals. So instead of having 8 of these, have 1,000,000 of them, right? If I had 1,000,000 of them, the little overlapping pieces that went outside or just missed on the inside would be so tiny that they'd be insignificant. And some of them would still even be canceling each other out, right? So making more and more subintervals makes this more and more accurate. Right? If I'd done it with only 2 subintervals, right? If I made a rectangle like this and then another rectangle like this, that'd be not a very good approximation. 8 of them is much better than having 2 of them. Yeah, definitely. All right, everybody good there? That's method number 2. We're going to practice all these methods on a couple of actual functions in a minute. But any questions so far? All right, our last method that we're going to use today also uses rectangles. Now let's think, we've done the left endpoints, we've done the right endpoints. What do you think we could use if we're still going to do rectangles that might make it even a little bit more accurate?
The midpoint.
The midpoint. Good. This is called the midpoint rectangular approximation method. So find the midpoint of each subinterval, find the value of the function there, and draw a rectangle using that. Oh, I totally missed that point. Good or no? And we'll note that once again, we've got some sections that are a little bit outside of our function and some that we are missing on the inside. Yeah? True? And some of those will cancel each other out. And we might also note that in this case, it's impossible to tell whether it's an under or an overestimate just from whether the function increases or decreases, because even on the increasing intervals, I've got some extra and I've got some that I missed, right? So we couldn't even do it on those. Good or no?
Good.
Wonderful. All right. those are the three types of approximations that we're going to do today. So we're going to practice that on a nice, simple, easy function. Okay. F of x equals x squared. So we're going to do a left, we're going to do a right, and we're going to do a midpoint rectangular approximation method to find the area under the curve from 0 to 3 using 3 subintervals. So if I am dividing up the section from 0 to 3 using 3 subintervals, what should each of those be? It should be from 0 to
1.
1, 1 to 2, and 2 to 3. Yeah. So let's start with a left approximation. So if I'm going to do a left rectangular approximation, I need to start at the leftmost endpoint of my interval, which is 0. And at 0, I go to the height of my function, which is what's the height
0.
of? Yeah, there we go. It's 0. And I draw a line straight across and drop back down to the x-axis. Well, that rectangle that I just drew doesn't even exist, does it? The height itself is 0, and the width of it is 1. There's our first one. What about the second one? We go to the left portion of the second little subinterval and go to the height of the function there. So 1 squared is 1. And draw your rectangle. What is the height of our rectangle? It's height of our rectangle is 1. The width of our rectangle is
1.
1. Great. Then we do the next subinterval between 2 to 3. So we go to the height of our function up here. What's the height of our function? What's the height of our function up here?
4.
4, which tells us that the height of that rectangle is 4. And what's its width?
1.
1. And what do we get when we add them all together?
5.
5 units squared. And clearly we know that this is an underestimate because why? We used a left rectangular approximation and our function was increasing, right? We left off a ton of space that was underneath here, didn't we? So in this case, that approximation was not very good at all. Would you agree with that?
Yeah.
Yeah. All right. Let's do a right approximation. So still 3 subintervals, 0 to 1, 1 to 2, 2 to 3. This time we go up to the height at the rightmost endpoint. What's the height of our function at its rightmost endpoint?
9.
9. So we go straight across for our subinterval and then straight down. What's the area of that rectangle? It's the width of 1 times the height of 9. Easy enough? What about the second one? It has a height of
4.
4 and a width of 1.
1.
And the last one should have a height of 1 and a width of 1. And what do we get? We get 14, which we know is an overestimate. And why do we know it's an overestimate? Because we've gone way over. Right? Not way over. Agreed or no?
Agreed.
All right. Cool. So on the left, we got 5. On the right, we got 14. Let's try to do a midpoint one. What do you think we're going to get? Probably something between 5 and 14. Yeah? Hopefully we get something between 5 and 14. So let's do our midpoint. Still going 0 to 1, 1 to 2, 2 to 3. What's the midpoint of 0 to 1?
0.5.
0.5, or I'm going to say a half, right? Right here. I'm going to go up to the value of my function and make a rectangle. The width is 1. In fact, the width for all of these is going to be 1, aren't they? 1, 1, and 1. And what's the height of our function when x equals 1/2?
A quarter.
Right, it's a quarter. It's 1/2 squared, right? And what about at this next one? At 3/2, we're going to go up and make our rectangle. And that should be 3/2 squared. And the last one should be 5/2 squared. And so when I add those all together, this is 1/4 plus 9/4 plus 25/4, which is 35/4, or 8 3/4, 8.75, which was definitely between 5 and 14, right? And we've got some sections that went over, right? And we've got some sections where we missed some pieces. Some of those will cancel out. And it looks like this approximation is quite a bit better than our other one. Yeah?
Yeah.
Yeah. Just for fun. How close? How much do you think we're off by? Any guesses how much we're off by?
A quarter.
You must have known the actual value was 9, huh?
Actually, I guessed. I
Oh,
felt
wow,
like
you
it.
guessed, and you were right. Yes, the actual value is 9. So the specific area underneath this curve is 9, right? And we got an approximation of 8.75 by using this midpoint approximation, which I feel like is, you know, pretty darn good, really, all things considered, right? Only off by a quarter, and we only use 3 subintervals. Imagine if we'd used 300 subintervals, how close we would be to the actual value, right? That's right. Yes, exactly. Good or no?
We're good.
All right. So what we're going to have you guys do then is I'm going to have you guys try to do one of these on your own. This one. Just do a midpoint approximation. So I want you to see if you can estimate the area underneath the curve 1 over x plus 1 from 1 to 9. And you're going to use 4 subintervals and a rectangular approximation. So I don't know if this will help you, but just for the heck of it, here is the graph on Desmos, and then I'll go just so you can see. I'm sure you can all graph it yourselves, but this is what we're looking for. The area between 1 and 9. So, you know, this section right here. An approximation for that using 4 subintervals and a midpoint approximation. You guys think you could do that?
Yes.
All right, I will give you 2 to 3 minutes and you should be able to successfully complete that. Ready, go.
Yeah.
All right, so hopefully, just to make sure, we had intervals from 1 to 3, 3 to 5, 5 to 7, and 7 to 9, each of which was 2 units, right? 2 units per interval. And so our midpoints of each one would have been at 2, 4, 6, and 8. Yeah? And so
Yeah.
the width of each one was 2, so we're going to have 2 times something plus 2 times something plus another 2 times something plus another 2 times something. And then inside of here, we should have had our value at 2, right? 1/2 plus 1. And then here we should have had 1/4 plus 1. And here we should have had 1/6 plus 1. And here we should have had 1/8 plus 1. Everybody agree with that? So this is 2 times 3/2, which is 3. This is 2 times 5/4, which is 5/2. This is 2 times 7/6, which is 7/3. And this is 2 times 9/8, which is 9/4. Good or no?
Good.
All right, and if we got a common denominator, it would have been the denominator of 12, which would be this 36 plus 30 plus 28 plus 27, which I think comes out to what, 121? Does that sound right? Or no?
Yeah.
Yep, and if we approximate that, that should be 10 point, a 12th, I think, is 0.083 repeating. Is that what you all got?
Wait, did you just estimate 121 over 12 in your head, or like did you already know the answer that it was in decimal form?
Well, I mean, I knew it was, it's 120 over 12, which is 10, right? So 10 and a 12th. I think I just, yeah. A 12th is 0.083 repeating. I'm pretty positive of that just from the number of times I've had to do division in my life. Is that, I think I'm right. Am I right or no?
It's right.
Oh, good. Okay. Yeah. I mean, I just did the 12th, but cool. Anybody not get that as their approximation? Oh, good. All right. So then the last thing I'm going to ask you is, does anybody know the exact value of the area underneath the curve there? Any of you gone ahead and learned all the things that you're supposed to learn later this year? Not all of them, but at least one thing. No? Anybody? No? All right. Well, then I'll tell you that the actual value is, I guess I should probably do it. Let's see. Should be 8 plus the natural log of 9. That's the actual exact value. And so somebody tell me, what does that approximate out to be?
10.197.
10.197 something. And so using 4 sub-intervals across a 9-unit long length of this, we're only off by, looks like, just over a tenth, a little more than a tenth of the unit, which is pretty good. Wouldn't you say? I think so. Cool. That's it. That's where we're going to stop today, because the next thing will take us more than the 8 minutes that we now have. So we'll be done with that. Any questions on that? All right.